Okay, we'll continue with our study of the hyperelastic response of solids, and in particular, we'll pick up with the idea we introduced the last time in the last segment, which is the idea of the material elastic tangent, right? Okay, so let's recall that. Okay, and of course all of this is with hyperelasticity, but I probably don't need to say that too much because we're not really looking at anything else, right? Okay, we're not looking at other descriptions of elasticity. Right, so here is our material elastic tangent. We decided to write it as C. It is defined as the derivative of the second Piola-Kirchhoff stress tensor with respect to the Lagrange strain tensor, all right? And now when we recall that we do indeed have a model of hyperelasticity, and therefore the stress itself is given to us as a derivative of a strain energy density function, right? In that manner, we see that the material elastic tangent is the second derivative of this strain energy density function with respect to the Lagrange strain tensor. Okay, and of course we saw that objectivity or frame indifference frame invariance, as I like to call it, implies that the strain energy density function psi, which can be written as psi function of f in general from this notion of hyperelasticity. We saw that frame invariance says that, well, it can depend upon f, that's all very well, but it can depend upon f only through the stretch tensor, the right stretch tensor. And once we have that dependence, we see that immediately it gives rise to other functional forms which must exist. C here is the right Cauchy-Green tensor. And finally, if we have that, we observed that we could also write it as some other function of the Lagrange strain tensor. Okay, and that is what allows us to carry out that sort of derivative. Okay, so let's look a little more closely at what this object does for us. There's a reason why it's called an elastic tangent. Essentially, it gives us the tangent to the material response. Okay, so let me write that down. It gives us really the tangent to the material response, and maybe we want to even think about this as the material response curve, although I'm going to put curve in quotes. It's not really necessary to put that word in quotes. Anyway, let me tell you what I mean by all this. All right, so essentially when we have a hyperelastic strain energy function, because of this sort of dependence, right, we know that we can now write the stress ultimately as a function of E. Okay, so we have this, essentially that functional dependence gives us the material response curve, so to speak. Of course, it is a curve in some many-dimensional space. S is symmetric, E is symmetric, so it's a curve in a six-dimensional space with an argument that is also six-dimensional. Okay? Nevertheless, we could conceptually draw a plot, right, So imagine that this is our higher dimensional space of E, okay? All right, and this is this axis represents our higher dimensional space of S. Okay, the material is nonlinear, so without really claiming to represent any particular material, let me give you a representative curve. It's nonlinear, so maybe it does something like that. Okay, that's our curve. So where does the tangent come into all this? Well, clearly it gives us the elastic tangent gives us the tangent to this curve if you just look at the definition back here, right? Okay, so in a sense that tangent is that. Okay, so this tangent is or more correctly, it's in some sense the slope of this tangent is given by C. All right, the elasticity tangent. Of course, all of this is sort of schematic, right, because we're working in a higher dimensional spaces. Nevertheless, okay, so what use is it? What it is useful for is that it gives us the material rate or the material time derivative of the stress. All right. In particular, from the chain rule, we can say that S dot equals partial of S with respect to E contracted with E dot all right, which of course from our definition of the elasticity tangent is that. Okay, in coordinate notation we have S dot ij equals C I j k l E E dot, and I don't need the underbar, E dot k l. Okay, this is what it's used for. If we look at that curve again, what we see is that as we march along the E-axis, right, we are increasing or varying the strain. The tangent essentially tells us how S varies, right? So it tells us essentially, it's the obvious thing, right? So it tells us that for every little increment, right? If you want to think about this as some delta E, it tells us what the corresponding, let me see if I can do this well, tells us what the corresponding delta S is, and if that change in E takes place over some time dt, then in the limit we get E dot, and then we get S dot as well. Okay, so this is what it's useful for. As we continue to deform the material, right, we have that setting, we deform the material, and as we're changing E, we know how the stress is changing as well. Okay, all right, all very good and very straightforward. Now, something I should point out is that the use of the qualifier material there refers not just to the fact that we're talking of some material, but also to the fact that S and E both live on the reference configuration, right? Right? S and E, as we've seen by construction, are properly defined on the reference configuration of the body, right? And we've seen that often we call the reference configuration interchangeably. We use the term the material configuration for it, and it is in this sense that we use the qualifier material when we talk of this elastic tangent. All right? Okay. Now that should have led to a question in your minds. Okay? If we have just written a tangent for material quantities defined on the reference configuration, what about quantities on the deformed or the current or the spatial configuration? Okay? So, what about equivalent ideas or equivalent quantities on omega sub t? Okay, and of course the natural thing to think about is, well, we have this guy, the Kirchhoff stress tau, right, which is obtained as a map forward, or as the term often is used in continuum mechanics, it is obtained as a push forward of S. Okay, so we have this object. Can we say anything about it? Right? Now the way I want to approach this problem is to say that what can we say about rates of this sort of a stress tensor? Can we come up with something like the material elastic tangent in this case? Now observe that we already have a conveniently defined strain rate, okay, which should be somewhat which is indeed analogous to E dot, plays the same role as E dot. We have something like that in the current configuration, right? So we have this. So besides the stress, we also have this quantity, right, D, which is, we saw that it is the symmetric component, symmetric part of the spatial velocity gradient tensor. Right, so just as we saw something between S dot and E dot, it's natural to ask whether we get something between these two objects, right? So this is the rate of deformation. Right? And I haven't shown it, but it's, as you may imagine, it's not very difficult to show that D is obtained by pushing E dot forward by some means, okay, using F. Right? You can write out that relation, but I'm not going to get into it right now. We don't need it for what we want to develop. So essentially we're asking, is there a relation now that goes between some sort of time derivative and so essentially what we want to know is, if I take a time derivative of tau, can I relate it to D? Okay, right, or really the other way around. Okay, is there something that relates them? Okay, now the natural thing to try here is to say, well, let's look at what happens with the time derivative. Okay, now of course tau is a spatial object, so you may say, all right, I can take the material time derivative of tau. Okay, so one may consider something like derivative of tau, time derivative of tau, remembering that x equals phi. All right? Indeed, one can compute this. But there is a problem, okay, which is that since tau is defined on the current configuration of the material, right, we have the current configuration, right, tau and D are defined there on the current configuration, and they would have been got to from some reference configuration, right? There is the further question that arises with respect to objects defined on the current configuration, And that question that arises is that of objectivity, right? Now what happens if you impose rigid body motions, right? So if you have a phi plus, right, which is c plus qx, what happens now to these objects, right? So I'm going to draw this, and because I want to draw a rigid motion, let me just draw this, and let's suppose it's sort of passed out of the board, okay, in the process of this rigid motion, okay? All right, it's gone. All right, so what happens now? So what we've seen is that what we've seen is that rigid body motions on omega t are of the form where the final configuration is c t plus q t acting on x, right? We have this sort of situation. Well, we know that because tau is a stress tensor defined on omega t, we know that now tau plus, right, the components of tau plus, right, the matrix components of tau plus will undergo a transformation as q tau q transpose, okay, because tau is objective, right? And the reason this follows is because you recall we showed this result for the Cauchy stress, right? We showed that sigma plus equals q sigma q transpose. Well, tau plus then is just q j sigma q transpose, right? Because this is tau. Okay? All right, and that's where we get that transformation rule for tau plus from. Okay, so this is what happens. So now a completely natural and actually an important question to ask is, well, what about this material time derivative? So after all, the material time derivative of tau, right, this object gives us back a tensor, right? And this tensor also belongs to omega t, right? It lives in the current configuration. So what we can ask now is, well, is this rate also objective? Okay? And that's important because, as you can imagine, now essentially what we're asking is the following, right? So we have the body in the reference configuration is deformed, gone to the current configuration, there's a stress there. And we are now talking of applying rigid motions on the current configuration. Okay, and we're asking, well, now how does tau change under those rigid motions, right? How do the components of tau change? All right. Now, an important question to ask is, well, can we come up with a material with some sort of derivative or some sort of rate which also transforms objectively, right? Because then we'll know how to write it out as the body undergoes its rigid motions. Okay. So the question to ask is, okay, is essentially the following, right? We can ask, if we take this time derivative, material time derivative of q tau q transpose x equals phi, which is the time derivative of tau plus all right. Okay. Does this also transform objectively? Is this in particular equal to q time derivative of tau material time derivative q transpose? right? Essentially, we're asking, does this material rate also transform objectively? Does it also do the right sort of thing? Because then we know how to write its components, all right? If you just carry out this derivative here, what you will see, however, is that this thing actually, if you compute this, what you will see is that you get an object which has the form q dot tau q transpose plus q okay. So we do get a one contribution which looks the way we would expect, right? That contribution does look like it's an objective transformation. But unfortunately, that's not the whole story. There's other stuff, right? There are these two terms which muddy the waters, right? And I say they muddy the waters because now what we're picking up, if you think about it, we're saying that, look, under current configuration, right? I'm applying rigid motions on the current configuration. I know how tau transforms, okay? And that part is quite clear. We know that tau transforms like shown here, okay? However, what we do not know is what happens with what happens now with the rate at which tau is changing, right? So when we compute this rate, we see that we get extra pieces. All right, and in particular, those extra pieces that we will get, which will be components of the rate of change of the transform tau, those extra pieces depend upon the rate at which we're applying this rigid motion. Okay, so what this says is that the components of the stress tensor that we get, okay, those components do not transform in an objective manner anymore when we are computing their rates. Okay. So what this means is that just taking this simple material time derivative of tau is not a good idea. Okay, we need to do something different. All right, and essentially the idea is that the material time derivative is not objective. So the material time derivative is not objective. Okay. Note, however, that D itself is objective, right? And we've shown this. Okay. Consequently, we cannot write a meaningful constitutive relation, right, of the following form, something relating this material time derivative to D, because whereas D transforms objectively, this time derivative on the left-hand side does not transform objectively. Okay, this guy is objective, this guy is not objective. All right. Okay, and it just means that if you try to start writing constitutive relations of this form between them in rate form, what we find is that we are always left with these q dots floating around, right? These terms that depend upon the rate at which we're applying this rigid motion, and it just becomes very difficult to write meaningful rates from them. Okay, we in particular remember the whole notion of constitutive response is that we don't want something where we pick up stress or stress rates which are affected simply by the fact that we're applying a motion here, right? A rigid motion, right? We want to get rid of that. Okay.